Right then, it's time to move on to SURDS. SURDS are kind of a funny word, people often laugh at it, but that's probably because they can't do them. And they're really easy. We've done indices, so all we need to do now is make that little step onto SURDS, which is to say anything with a square root e. So, as I said, anything which has a square root is a surd. Now I'm saying that a square root is not like square root of 4 because that's just 2. Anything which can't be reduced to some sort of quotient or integer. So surds are any real number which aren't quotients or integers, obviously, or natural numbers by extension. So let's just make that into a little statement. Then we're going to go on to what we do with surds to make them kind of simpler and easier to digest. So, right, what I've written here is that, whoa, plug. I've written that surds are any number that can only be expressed as a square root or a half power. Now, I'm saying square root, but we can also say cube root, and this would be a third power, but for now I'm just saying square root just to be simple. So as an example, root 2. Now you can stick root 2 into your calculator, you get 1.4 something, but that's not exact. That's only exact to the accuracy that your calculator displays it. Now root 2 is irrational, meaning that it can't be expressed as a rational number, as in a fraction. So we're never actually going to be able to get an exact number as a decimal. So that's why we just leave it like that. That's a surd. Also, something like 1 plus root 3. That's still a surd. We've got 1 and then this little root 3 here. Still a surd. Something else like 1 over root 5. That's also a surd. What's not a surd is something like root 4. Why is it not a surd? Because, as I said, that's just equal to 2. So we're only looking at these ones, but when we use them, we can simplify them down. So if you were given one like root 27, what you were expected to do is to be able to break this down into a smaller surd, because you want the smallest number possible under that root sign. The way that you do this is using factors. Again, it's always factors. And also those laws of indices that we previously spoke about, you know, like where you'd be having it to the power of something and then those would combine together under that. So, let's have a go at this example. I want my blue pen. "27 is a product of 9 and 3. So what we can do is we can write it as that. Now this is just using that law of indices where that would be to the power of a half. So if all of that is to a power of a half, then that half applies to each one under there. So it becomes that. Now it's good that we did it with 9 and 3 because 9 is a square number, so we can just turn that root 9 into 3 root 3. That's simplifying it. So this is, let's do a little title. This is where we simplify. Let's do another example. Right, root 32. Same thing again, we're going to break this down into 2 factors. We're going to choose 2 factors which one of them is a square. We want like a really high square. So 32, like we could do 8 and 4, but we want the highest square factor as possible. So we're going to go with actually 16 and 2. So then you've got 16 square rooted times by root 2. So then we get 4 root 2. Notice if we did it the other way, if we went with 8 and 4, this would then equal root 8 times root 4, which is equal to 2 root 8. Thing about that is that you want to make this under the square root as small as possible. 8 is not as small as 2, so we would prefer to do this option. Choose the squared factor to be as big as possible. Then just go from there. Now, let's try another example. Right, this time we've got this little algebraic expression, 1 plus root 2 squared. To simplify that, we're going to get rid of those brackets. So, normal situation, you could do your little grid, can't you? You could be like 1 root 2, 1 root 2, 1 times 1 is 1, 1 root 2, root 2, root 2. Root 2 times root 2 is 2. So then you get 1 plus 2 root 2 plus 3, which is obviously just equal to 4 plus 2 lots of root 2. Easy as that. Okay, how about this one? We're just going to change this slightly. Rather than being a square, we're going to do 1 plus root 2 times by 1 minus root 2. What we'll see from this is that this is actually called a difference of two squares, what it comes out to, and we'll come up to that in a minute. Because if we do the same little grid here, but we swap that for a minus, that means that's a minus, and that's a minus. These two are then going to cancel out. So what this equals to is 1 minus 2, which is equal to minus 1, which is no longer a surd. So when you times these two together, don't get a surd anymore. Nice. So there's one more that I want to cover, and this is where you're given us two surds or something and you are told to write it in a certain form. So this question is where you're given this little expression and you're told to write it as root a, which is to say write it as the root of one thing rather than these two. So first things first, we need to get these as the root of the same thing. We can't make this any smaller, so we're going to look at this. We're going to see if this can be some version of root 2. So root 8 equals root of 4 times 2, which is 2 root 2. So then this becomes 2 root 2 plus 2 root 2, 2 root 2 plus root 2, which is equal to 3 root 2. Which, we're not finished, we need it as just the root of one thing, which is equal to root 9 times root 2, which is equal to root 18. Bada bing, bada boom. So this is how to simplify surds. I've left all this space because what we're going to do next is we're going to look at rationalising the denominator. Now that's the other trick that you need to know at A level. We've got simplify, then we've got rationalising the denominator, which is to say don't have any square roots in the denominator. So as I said, rationalising the denominator is when you remove any surds from the denominator. That's essentially it. So, I'll just put that in a quick sentence. So let's have a little example, e.g. Let's just go stupidly easy, 1 over root 2. The ring. 1 over root 2 is probably the simplest irrational fraction that we could have. Now, when you want to change this, we kind of have to be smart about what we do. We can't times it by like root 2 because that's going to make it another fraction. So what we do is we times it by the best thing ever, which is 1. You just times it by 1. But this is where you're smart. You don't times it by 1, you times it by something which cancels to 1. i.e. you times it by root 2 over root 2. Obviously that cancels to 1, so it's not going to actually change numerically what the expression means, but it means that this now equals, it's going to be root 2 on the top, then on the bottom it's root 2 times root 2, which is just 2. You've rationalised it. Bam. Done. Is that it? We're done? No, we're not done because it gets a little bit harder. So let's do another example. This one now has a bit on the bottom which looks a bit tricky. If we times this by the denominator, like we did in the previous one, we're not actually going to get a rational denominator because, like here, if we just squared a surd like this, you still get a surd. But notice here, we actually got a rational. So we got rid of the surd. So what we're going to do here is we're going to times it by the exact same as the denominator, but changing one of the signs. So we're still going to do it on top and bottom. So we times it by this, root 3 plus 4, instead of root 3 minus 4, over root 3 plus 4. The point of that is that you're using a really good trick here. Now right at the top, so if you have two squares and you do one minus the other, that is equal to, always equal to, a plus b times by a minus b. Now this is called the difference of two squares. So called for obvious reasons because you've got the difference of two squares, the difference between a squared and b squared. And it's always equal to that. It's an identity, always, always true. That is what we're doing right here. We're just applying this to here because we're going to times these two together. So what we're going to get on the bottom is this difference of two squares. So you're going to get root 3 squared, which is 3. Then you're going to get this 4 squared, which is 16. That's the answer to that. Now, does it get much harder than this? It does. We could go in one further with a very simple and similar example. So if you had this, similar situation as previous, you're going to times it by the same as the bottom, but with a flipped sign. Now, it doesn't matter if you flip it on the -5 or the -2, as long as you only do it on one of them. I'm going to choose flipping that -2 to a plus, so that would be root 5 plus root 2. Bam, that's another one. Now let's look for something which is much more difficult. Okay, we've got our last one. Yeah, this is a difficult one. Find a and b such that a root b plus b root a equals 90 root 3. Now this is really the final brain scratcher of this little lesson that we're doing. This is probably as tough as it would get in A level. What you need to do here is notice that root 3 has to be a common, like a simplified version of both root b and root a, because when you add them, you're getting just that by itself. So what you would then have to do is say, well, root b must be something times root 3, root a must be something else, but still times by root 3. So Yeah, so what you get here, are we still on the screen? Yeah, only just. So we know that this root a must be some multiple of root 3. Root b must also be some multiple of root 3. So I've written those as x root 3 and y root 3. So when we work out a, we just square all of this, and it's that. We square all of b, and it's that. You then just plug all that into there, and you find your final answer. Now your final answer is, I'll tell you what, you can do it. Just stick them in there and you'll find out some answers. It's gonna be, I don't want to leave it hanging. Okay, just do it quickly. That's the final answer. You need to check it out. Now, one last little piece. To quote Columba, one last thing is that in A level, you need to be aware that the square root of something isn't always the positive number. If, where can I write this? If you do the square root of x and it doesn't have anything in front of the square root, that just implies it's the positive root. However, but x squared equals a, for example, implies that actually x is the plus or minus square root of a. Now that's a really common problem that people run into, is that they forget the plus or minus root of something. So, what have we got left? This is really important. Your difference of two squares is really important. And all you need to do is practice rationalising and simplifying. Now they're both really easy if you understand indices. They're really easy anyway. And that's it. That's it for indices and surds. Next time we get to move on to quadratics and polynomials. All right. Long video.